We're going to break this solution into 3 steps. Step 1 is the reduction. We'll prove that it suffices to consider the cases when this k-dimensional ball is contained in -1 to 1 n-fold Cartesian product and centered at the origin. This is a subtle part, which is intuitively correct, but hard to prove formally. Why is it intuitively correct? This is because just consider a case when n is equal to 2. And we are looking at this 2-dimensional square whose side lengths are equal to 2. And now you consider all the possible 1-dimensional balls, which are really 1-dimensional length segments contained in this cube of side length 2. To maximize the length of those line segments, you would expect when the line segment is symmetric around the origin, then it could possibly reach its maximality. But we have to prove this more formally. Indeed, let Bxr be the ball of radius r centered at x. That is contained in this cube. And let r sub x from Rn to Rn be the reflection about x. Using mathematical notations, what I mean is that this map sends a vector y to 2x minus y. It sends a vector to the other side of the point x. This is a reflection because if you add y and the vector 2x minus y and divide the sum by 2, you get back x. So x is in the midpoint of those 2 points. Then we consider this map Rx applied to this cube. What we get is the set of points 2x minus y, where y is in this cube. So this is a reflection of this cube with respect to the point x. But on the other hand, we know this ball centered at x with radius r is already symmetric about x. The point is in this ball if and only if 2x minus that point is in this ball. So from this we know Bxr by the symmetry equal to Rx of B of xr is contained in the reflection of this cube. Because this ball, by assumption, is contained in this cube. So this ball must be contained in the section of this cube and its reflection. And now let us look at this intersection. What is it? Okay, now, what is the geometric meaning of this intersection? If this is this cube, and this point is the x, now we're going to do this reflection of the cube about X. And it is not hard to see this reflection is again a cube, which can be viewed as a translation of the original cube. Now the intersection is this shaded region. And use mathematical terminology, this is a rectangular parallelepiped centered at X, whose side lengths are all less than or equal to 2. And now, this radius r is less than or equal to the maximum of S, where S is the radius of this ball centered at X that is contained in this intersection. For convenience, let's call this intersection RP, rectangular parallelepiped. So it's RP and RP. Because this ball centered at X with radius r is contained in this RP, then this r must be less than or equal to the maximum possible number, which can be the radius of a ball centered at X that is contained in RP. And this is further less than or equal to the max of such balls with radius S contained in the translation of this cube of side length 2 by X. The geometric meaning of this is the cube centered at X with side length 2. This inequality follows from the fact that the side lengths of RP are all less than or equal to 2. Now if you perform a translation, you can replace this X by the origin, 0. So this is equal to the maximum of S for the ball centered at the origin with radius S that is contained in the cube at the origin with side length 2. Hence, we have the max of R BXR contained in this cube is less than or equal to max of S is B0S contained in this cube. This is because here R is arbitrary. This R is any ball centered at X with radius R that is contained in this cube centered at 0 with side length 2. By the arbitrariness, we have this inequality. And this finishes our step number 1, the reduction. We have reduced the problem to the situation where it suffices to consider those balls that are centered at the origin and contained in this cube centered at the origin with side length 2.